Introduction to AES CBC mode. Welcome to the channel. Please consider subscribing. I produce videos daily covering a wide variety of cloud topics with focus on networking. Also, hit the bell icon to get notified of new videos. Today we're diving deep into one of the most fundamental cryptographic constructions in modern secure communications, the Advanced Encryption Standard in Cipher Block Chaining mode, commonly known as AES CBC. This presentation is designed for those who already have a basic understanding of symmetric cryptography and block ciphers, and are ready to explore the mathematical foundations and operational mechanics that make CBC mode both powerful and secure when properly implemented. AES CBC has been a cornerstone of data encryption for decades, protecting everything from HTTPS connections to encrypted file systems. Understanding how it works at a mathematical level is crucial for security engineers, cryptography practitioners, and anyone implementing secure systems. Throughout this presentation, we will build from fundamental concepts to complex operational details, ensuring you understand not just what CBC mode is, but why it does it and what can go wrong if implemented incorrectly. What is AES? Let's begin with the foundation. The Advanced Encryption Standard itself. AES is not a mode of operation. It's the underlying block cipher that provides the actual encryption transformation. Think of AES as the engine and CBC as the transmission system that determines how that engine is used to process data. AES was selected by the National Institute of Standards and Technology in 2001 after a rigorous 5-year competition that evaluated multiple candidate algorithms based on security, performance, and implementation characteristics. AES operates on fixed-size blocks of 128 bits, which equals 16 bytes. This is an absolutely critical specification. No matter what size your plaintext is, AES will always process it in these fixed 128-bit chunks. The algorithm accepts 3 key sizes: 128 bits, 192 bits, or 256 bits. The key size determines how many rounds of transformation are applied during encryption. A 128-bit key uses 10 rounds, a 192-bit key uses 12 rounds, and a 256-bit key uses 14 rounds. Each round applies a series of mathematical transformations, including byte substitution, row shifting, column mixing, and round key addition. The symmetric nature of AES means the same key is used for both encryption and decryption. This stands in contrast to asymmetric algorithms like RSA, where different keys are used for encryption and decryption. The symmetric property makes AES extremely fast and efficient, but it also introduces the key distribution problem. How do both parties securely obtain the same secret key? This is typically solved through key exchange protocols like Diffie-Hellman or by using asymmetric cryptography to establish a shared symmetric key. Understanding block cipher modes. Now that we understand AES as a block cipher, we need to address a fundamental question. Why do we need modes of operation at all? The answer lies in the limitations of raw block cipher operation, often called electronic codebook mode, or ECB. When you use a block cipher in ECB mode, each block of plaintext is independently encrypted with the same key. This creates a serious security vulnerability. Identical plaintext blocks always produce identical ciphertext blocks. Imagine encrypting a document with repeated content, like a database dump with many null values or an image with large areas of solid color. In ECB mode, these repeated patterns would be visible in the ciphertext. An attacker analyzing the ciphertext could detect these patterns and make inferences about the plaintext structure without breaking the encryption itself. This is not theoretical. The famous ECB penguin image demonstrates how encrypting a bitmap image with ECB mode reveals the original image's outline in the encrypted version. Modes of operation solve this problem by introducing dependencies between blocks. Instead of encrypting each block independently, a mode like CBC creates a chain where each ciphertext block depends on all previous plaintext blocks. This means that even if you have identical plaintext blocks at different positions in your message, they will encrypt to completely different ciphertext blocks. This property, called semantic security, is essential for modern cryptographic systems. Beyond just hiding patterns, modes of operation also address practical concerns like how to handle messages that aren't exact multiples of the block size, how to enable parallel processing for performance, and how to provide authentication in addition to confidentiality. Different modes like CTR, GCM, and CBC each make different trade-offs between security properties, performance characteristics, and implementation complexity. Introducing Cipher Block Chaining. Cipher Block Chaining, or CBC, is one of the earliest and most widely deployed block cipher modes. Designed to address the pattern leakage problem of ECB mode, CBC introduces a chaining mechanism where each plaintext block is XORed with the previous ciphertext block before encryption. This creates an avalanche effect where a change in any plaintext block affects all subsequent ciphertext blocks, providing the semantic security we need. The name Cipher Block Chaining perfectly describes the mechanism. Each block of ciphertext is chained to the next block's encryption process. When you encrypt block 2, you first XOR its plaintext with block 1's ciphertext before applying AES encryption. When you encrypt block 3, you XOR with block 2's ciphertext, and so on. This creates a dependency chain throughout the entire message. But there's an immediate question. What about the very first block? There's no previous ciphertext to XOR with. This is where the initialization vector, or IV, comes in. The IV serves as a synthetic previous ciphertext block for the first real plaintext block. It's a random 128-bit value, the same size as an AES block, that must be unique for every message encrypted with the same key. We'll explore the critical importance of IV selection in detail later, as improper IV usage is one of the most common implementation vulnerabilities in CBC mode. CBC mode has been extensively analyzed and is proven secure under certain conditions. It provides confidentiality for data and hides patterns effectively. However, CBC is a confidentiality-only mode. It does not provide authentication or integrity protection. If you need authenticated encryption, you must either use an authenticated encryption mode like GCM or AES CCM, or combine CBC with a separate MAC algorithm in an encrypt then MAC construction. Mathematical notation and components. Before we dive into the encryption and decryption formulas, let's establish our mathematical notation and ensure we understand each component. Using precise notation is crucial when discussing cryptographic algorithms because ambiguity can lead to implementation errors that compromise security. We'll use standard cryptographic notation that you'll encounter in academic papers and technical specifications. First, let's define our plaintext message. We denote the complete message as a sequence of plaintext blocks, P1, P2, P3, and so on, up through Pn, where n represents the total number of blocks. Each of these blocks is exactly 128 bits in size. If your original message isn't a multiple of 128 bits, you must apply padding before encryption. Common padding schemes, for example, PKCS number 7, add bytes that indicate the number of padding bytes added. Similarly, we denote the ciphertext as C1, C2, C3, up to Cn. Each ciphertext block is also 128 bits, matching the block size of AES. This is a fundamental property of block ciphers. The output size always equals the input size. The key is denoted as K, and while it could be 128, 192, or 256 bits depending on your AES variant, this does not affect the CBC mode operation itself. The initialization vector, denoted as IV, must be exactly 128 bits, matching the AES block size. The encryption function is written as E sub k, which reads as encryption with key k. When we write E sub k of x, it means to encrypt block x using AES with key k. Similarly, D sub k of x means to decrypt block x using AES with key k. The XOR operation, which is critical to CBC mode, is denoted by the XOR symbol. XOR is bitwise exclusive OR. For each bit position, the output is 1 if the inputs differ, and 0 if they are the same. CBC encryption formula. Now we're ready to examine the mathematical definition of CBC encryption. The encryption process consists of two formulas, one for the first block, which uses the IV, and one for all subsequent blocks, which use the previous ciphertext. Understanding these formulas is essential because they define exactly what operations must be performed and in what order. For the first block, the encryption formula is C1 equals E underscore K applied to the quantity P1 XOR I versus. Let's break this down step by step. First, we take our first plaintext block P1 and perform a bitwise XOR with the initialization vector IV. Remember, both P1 and IV are 128-bit values, so this is a straightforward bit-by-bit XOR operation. The result of this XOR is a 128-bit intermediate value that we then feed into the AES encryption function using key k. The output of this encryption is our first ciphertext block C1. For every subsequent block where I is greater than 1, the formula is C subscript I equals E subscript K applied to the quantity P subscript IX or C subscript I minus 1. This is the chaining mechanism that gives CBC its name. To encrypt the second block, we XOR P2 with C1, the ciphertext we just produced from the first block. To encrypt the third block, we XOR P3 with C2, and so forth. Each encryption depends on the previous ciphertext, creating a chain of dependencies. This chaining property has profound implications for security and performance. On the security side, it means that identical plaintext blocks in different positions will encrypt to different ciphertext blocks because they are being XO-read with different previous ciphertext values. On the performance side, it means encryption cannot be parallelized. You must finish encrypting block I before you can start encrypting block I plus 1, because you need CI as input. This sequential nature makes CBC encryption slower on modern multi-core systems compared to modes like CTR that allow parallel processing. Visualizing CBC encryption. To truly understand CBC mode, we need to visualize the encryption process as a flow of data through XOR operations and AES encryption steps. The diagram shown demonstrates the complete encryption chain for multiple blocks, illustrating how each component feeds into the next. Let's walk through this process block by block to build intuition for how the chaining mechanism works. The process begins with our initialization vector and first plaintext block. The IV and P1 are combined using XOR, which produces an intermediate value. This intermediate value then enters the AES encryption function, along with our secret key K. The AES function performs its rounds of substitution, permutation, and mixing, which ultimately produces our first ciphertext block C1. This C1 is now used in two ways. It is part of our output ciphertext that we send to the recipient, and it is also fed back into the encryption process for the next block. For the second block, we take P2 and XOR it with C1. Notice how C1, which was just produced by encrypting the first block, now influences the encryption of the second block. This XOR result goes through AES encryption with key K, producing C2. Again, C2 serves dual purposes. It is part of our output, and it becomes input for encrypting the third block. This pattern continues throughout the message. The visual representation makes clear why this is called chaining. There is a direct chain of dependencies from each ciphertext block to the next encryption operation. If we were to change even a single bit in P1, it would change C1, which would change how P2 is encrypted, which would change C2, which would affect P3's encryption, and so on. This avalanche effect is exactly what we want for semantic security. CBC decryption formula. Decryption in CBC mode follows a symmetric but slightly different process than encryption. The formulas are mirror images that reverse the encryption operations, but with an important difference. Decryption can be parallelized while encryption cannot. Let's examine the mathematical formulas for CBC decryption and understand why this parallelization property exists. For the first block, the decryption formula is P1 equals D_K applied to C1, and then XOR that result with IB. Notice the order of operations here. We first decrypt the ciphertext block using AES decryption with key K, producing an intermediate value. And then we XOR that intermediate value with the initialization vector. This is the reverse of encryption, where we XO read first and then encrypted. For all subsequent blocks where I is greater than 1, the formula is Pi equals DK applied to Ci, XOR with C sub I minus 1. To recover plaintext block 2, we decrypt C2 using AES decryption, then XOR the result with C1. To recover P3, we decrypt C3 and XOR with C2, and this pattern continues. The key insight is that we XOR with the previous ciphertext block, not with any value we've just computed. This difference from encryption has a crucial performance implication. During decryption, we already have all the ciphertext blocks available before we start. This means we can decrypt C1, C2, C3, and so on simultaneously on different processor cores. Each decryption only depends on the ciphertext blocks, which we already possess, not on any previously decrypted plaintext. After the parallel AES decryption operations complete, we can then perform the XOR operations with the previous ciphertext blocks to recover the plaintext. This asymmetry between encryption and decryption performance is one of CBC's characteristics. While encryption must be sequential, decryption can be highly parallel on modern hardware. This makes CBC more suitable for scenarios where decryption speed is more critical than encryption speed, such as in certain streaming protocols or when serving encrypted content to many clients. Visualizing CBC decryption. The decryption diagram mirrors the encryption process but flows in reverse. Visualizing this reverse flow helps solidify understanding of how CBC mode maintains the ability to recover plaintext from ciphertext while preserving the security properties we need. Let's trace through the decryption of a multi-block message to see how each component interacts. Decryption begins when we receive the complete ciphertext sequence C1, C2, C3, and so on, along with the IB. Remember, the IB must be transmitted alongside the ciphertext. It is not secret, so this does not compromise security. To recover the first plaintext block, we take C1 and apply AES decryption with key K. This produces an intermediate value, which we then XOR with the IB to recover P1. For the second block, we take C2 and apply AES decryption with key K, producing another intermediate value. We then XOR this with C1 to recover P2. Notice that C1 appears in two places. It was decrypted to help recover P1, and it is used as XOR input to recover P2. This reuse of ciphertext blocks is what enables parallel decryption, since we have access to all C values before starting any decryption operations. The diagram clearly shows the independence of the AES decryption operations. Unlike encryption where each AES operation must wait for the previous one to complete, all the AES decryption boxes can execute simultaneously. Only after these decryptions complete do we need to perform the XOR operations with the previous ciphertext blocks. This two-phase approach, parallel AES decryption followed by XOR combination, is how implementations achieve high decryption throughput on multi-core processors. The critical role of the IV. The initialization vector is arguably the most critical component of CBC mode security, and it is also the most commonly misunderstood and misused. An IV in CBC mode must satisfy two essential properties. It must be unpredictable, and it must be unique for each message encrypted with the same key. Let us explore why these properties are necessary and what happens when they are violated. The unpredictability requirement means the IV must be generated using a cryptographically secure random number generator. It's not sufficient for the IV to merely be unique. It must be impossible for an attacker to predict what IV will be used for the next encryption operation. This is because an attacker who can predict the next IV can potentially craft chosen plaintext attacks that reveal information about previous encryptions. The uniqueness requirement means you must never encrypt two different messages with the same key IV pair. If you reuse an IV with the same key, the security of CBC mode breaks down completely for the first block, and patterns between messages become visible. Think about what happens if you encrypt two messages with the same IV and key, and both messages start with the same plaintext block, then both will produce the same first ciphertext block. This immediately leaks information to an attacker. The IV does not need to be kept secret. In fact, it must be transmitted alongside the ciphertext so the recipient can decrypt the message. Typically, the IV is prepended to the ciphertext as the first 16 bytes of the transmission. Since it is not secret, generating the IV is easier than generating keys. You do not need to worry about secure key distribution for I verses. However, you absolutely must ensure proper random generation and never reuse an IV. Security implications of IV reuse. Let's examine mathematically what happens when an IV is reused, because understanding this vulnerability helps illustrate why the IV requirements are so strict. Suppose an attacker knows we've encrypted two different messages using the same key K and the same I verses. Let's call these messages A and B, with their first plaintext blocks being A1 and B1. What can the attacker learn? For message A, the first ciphertext block is CA1 equals EK applied to A1 XOR IV. For message B, the first ciphertext block is CB1 equals EK applied to B1 XOR IV. Both of these ciphertext blocks are visible to an attacker since they are transmitted over the network. Now, remember that AES is a deterministic function. The same input always produces the same output. This means if A1 XOR IV equals B1 XOR IV, then CA1 will equal CB1. Rearranging that equation, A1 XOR IV equals B1 XOR IV implies that A1 equals B1. So by simply observing whether the first ciphertext blocks are identical, the attacker immediately learns whether the first plaintext blocks of two messages are the same. This is a complete break of semantic security for the first block. Even worse, if the attacker knows one of the plain texts, say A1, they can immediately recover B1 by exploiting the relationship between the ciphertexts. The vulnerability extends beyond just the first block. While subsequent blocks use previous ciphertext in their chaining, the damage is done. The attacker has learned something about the plaintext by examining only the ciphertext, which violates the fundamental security property we need from encryption. This is why proper IV generation is not optional or a best practice. It is an absolute requirement for secure CBC operation. Proper IV generation and management. Given the critical importance of proper IV handling, let's discuss the correct approaches to generating and managing IVs in CBC mode implementations. The gold standard is to use a cryptographically secure pseudo-random number generator, often abbreviated as CSPRNG, to generate a fresh random 128-bit value for every encryption operation. Most programming languages and cryptographic libraries provide CSPRNGs. In Linux systems, reading from /dev/u random provides cryptographically secure random bytes. In Windows, the cryptgen random function serves this purpose. Modern languages like Python offer secrets.token bytes, while Java provides secure random. It's crucial to use these specialized functions rather than standard random number generators like rand or math.random, which are not cryptographically secure and can be predicted. An alternative approach used in some protocols is to derive the IV from a nonce and a counter. For example, TLS 1.1 and 1.2 use a scheme where each party maintains a counter that increments with each message, and this counter is used as or combined into the IV. This approach can work if implemented correctly, but it requires careful state management to ensure the counter never repeats. One common mistake is attempting to use a hash of the plaintext as the IV, thinking this provides both uniqueness and some connection to the data being encrypted. This is dangerous because it makes the IV predictable if the attacker knows or can guess the plaintext. Another mistake is using a timestamp as the IV. While timestamps might seem unique, they're highly predictable and can repeat if multiple encryptions happen within the same time quantum. Always use a CSPRNG unless you have a specific protocol requirement and deeply understand the security implications. The chaining property in detail. The chaining property is CBC mode's defining characteristic and the source of both its security benefits and its performance limitations. Let's explore this property in depth to understand exactly how dependencies propagate through the encryption process and what this means for security and implementation. When we say CBC has a chaining property, we mean that each ciphertext block cryptographically depends on all previous plaintext blocks. Consider encrypting a 4-block message. The first ciphertext C1 depends on P1 and the IV. The second ciphertext C2 depends on P2 and C1, but since C1 depends on P1, we can say C2 indirectly depends on both P1 and P2. Similarly, C3 depends directly on P3 and C2, which means it indirectly depends on P1, P2, and P3. This cascading dependency has a crucial security implication. If you modify any bit anywhere in the plaintext, all ciphertext blocks from that position onward will change completely. This is called the avalanche effect. Suppose you flip a single bit in the second plaintext block P2. This changes the XOR input to the AES encryption of P2, which changes C2 entirely due to AES's diffusion properties. But C2 is then used as XOR input for encrypting P3, so C3 changes entirely as well. And C3 is used for encrypting P4, so C4 changes, and so on to the end of the message. This avalanche effect prevents an attacker from making controlled modifications to the plaintext by manipulating the ciphertext. If CBC didn't have this property, an attacker could flip specific bits in the ciphertext to cause predictable changes in the plaintext upon decryption. With CBC, any change to any ciphertext block causes unpredictable, widespread changes throughout the decrypted plaintext. However, the chaining property also means encryption cannot be parallelized. Each encryption operation must complete before the next can begin because each needs the previous ciphertext as input. This is a significant performance limitation on modern multi-core processors where parallel execution is key to achieving high throughput. This is why modes like CTR and GCM, which allow parallel operation, are increasingly preferred for high-performance applications. Avalanche effect demonstration. To really drive home the importance of the avalanche effect, let's walk through a concrete example showing how a single bit change propagates through CBC encryption. Understanding this behavior at a detailed level helps appreciate why CBC provides the security properties it does and why certain attacks against CBC modes are or aren't possible. Imagine we have a message with 3 blocks, P1, P2, and P3. We encrypt this message using CBC with some key K and IV, producing ciphertext blocks C1, C2, and C3. Now, let's say we prepare to encrypt the same message again with the same key and IV, but this time, we flip a single bit in the second plaintext block P2. What happens? The encryption of the first block is identical. P1 hasn't changed, the IV hasn't changed, and the key hasn't changed, so C1 is exactly the same as before. But when we reach the second block, something different happens. The modified P2 is XOR-read with C1 just like before, but this XOR result is now different because P2 is different. This different value enters AES encryption. and due to AES's strong avalanche effect within the cipher itself, the resulting C2 is completely different from the original C2, with approximately half the bits flipped. Now when we encrypt the third block, P3 hasn't changed, but we're XORing it with a completely different C2. This produces a different input to AES encryption for the third block, resulting in a completely different C3 as well. In fact, C3 will differ from the original C3 in approximately half its bits, despite the fact that P3 itself was never modified. This demonstrates the avalanche effect in action. A single bit change in P2 caused C2 and all subsequent ciphertext blocks to change completely. This behavior is exactly what we want for security. It means an attacker cannot make targeted modifications to the ciphertext to achieve predictable changes in the plaintext. Any modification to the ciphertext will either be detected as authentication failure if we're using authenticated encryption, or will cause essentially random corruption in the decrypted plaintext if we're not using authentication. Padding requirements in CBC mode. So far, we've assumed our plaintext divides evenly into 128-bit blocks. But in reality, most messages aren't exact multiples of 16 bytes. This creates a practical problem. What do we do with the final, partial block? The answer is padding. The choice of padding scheme has both functional and security implications. Let's examine the most common padding scheme used with CBC, PKCS 7 padding. PKCS 7 padding, defined in RFC 5652, works as follows. If we need to add n bytes of padding to reach a full block, we add n bytes, each with the value n. For example, if our message ends with 11 bytes of data and we need 5 more bytes to complete a 16-byte block, we add 5 bytes, each containing the value 5. If we need to add 1 byte, we add 1 byte containing the value 1. If we need to add 15 bytes, we add 15 bytes each containing the value 15. But what if our message is already an exact multiple of the block size? In this case, we must still add padding, a full block of padding. We add 16 bytes, each containing the value 16. This might seem wasteful, but it is necessary to make the padding unambiguous. When decrypting, we look at the last byte of the last decrypted block, interpret it as n, and remove the last n bytes. Without adding a full block when the message is already block aligned, we would not be able to distinguish between actual data and padding. Padding has security implications beyond just making the math work. Improper padding validation has led to serious vulnerabilities like the padding oracle attack, which we will discuss shortly. The decryptor must carefully validate that the padding is correct. The last byte's value n must be between 1 and 16, and the last n bytes must all contain the value n. If this validation fails, the implementation should return a generic decryption error, not a specific padding error, to avoid leaking information to attackers. CBC mode vulnerabilities, padding oracle attacks. While CBC mode itself is cryptographically sound when used correctly, improper implementations have led to devastating attacks. The most famous is the padding oracle attack, discovered by Serge Vatanay in 2002. This attack demonstrates why implementation details matter just as much as the underlying cryptographic algorithms. Understanding padding oracle attacks is essential for anyone implementing or auditing CBC-based systems. A padding oracle attack exploits a subtle information leak that occurs when a system reveals whether padding validation succeeded or failed. Imagine a web application that uses CBC encryption. When it receives an encrypted request, it decrypts it and validates the padding. If the padding is invalid, it returns a padding error message or shows different timing behavior. If the padding is valid but the plaintext is malformed in some other way, it returns a different error. This difference in behavior is the oracle. It answers the question, was the padding valid? An attacker can exploit this oracle to decrypt ciphertext without knowing the key. Here is how. Remember that in CBC decryption, pi equals d subscript k applied to c subscript I, XOR with c subscript I minus 1. The attacker does not know the output of d subscript k, but they control c subscript I minus 1. By systematically modifying bytes in c subscript I minus 1 and observing whether the padding is valid, they can deduce information about the output of d subscript k, which eventually reveals pi. The attack works block by block, byte by byte. For a 128-bit block, the attacker needs to make an average of 128 queries per byte, or about 2048 queries per block. While this might seem like a lot, it is entirely feasible in practice. The original Botany paper showed how to decrypt secure sockets layer/TLS traffic. Later, researchers demonstrated practical attacks against ASP.NET, Java Server Faces, Ruby on Rails, and many other frameworks that used CBC mode with distinguishable padding errors. The lesson is clear. Implementations must never reveal whether a padding error occurred. Instead, they should perform padding validation in constant time and return generic decryption failed errors that don't distinguish between padding errors, MAC verification failures, or other problems. Better yet, use authenticated encryption modes like GCM that don't have padding and include built-in authentication, eliminating the conditions that make padding oracle attacks possible. CBC mode vulnerabilities, bit flipping attacks. Another important vulnerability class for CBC mode is bit flipping attacks. These attacks exploit the fact that CBC mode provides confidentiality but not authentication. If you are using CBC without a separate MAC, an attacker can make controlled modifications to the ciphertext that cause predictable changes to the decrypted plaintext. Let us understand how this works mathematically and why it is dangerous. Recall the decryption formula. P sub I equals D sub K applied to C sub I, XOR D with C sub I minus 1. Notice that the attacker can modify C sub I minus 1, and this modification will be XOR D directly into the recovered plaintext P sub I if an attacker flips bit J in C sub I minus 1. Bit J in P sub I will also flip after decryption. This gives the attacker precise control over specific bits in the plaintext, even though they do not know the key. Here's a concrete attack scenario. Suppose an application encrypts user commands using CBC without authentication. A legitimate encrypted command might decrypt to something like transfer 100 to Bob. The attacker intercepts this ciphertext and wants to change it to transfer 999 to Bob. They don't need to decrypt anything. They just need to identify which ciphertext block, when decrypted, will contain the bytes 100, then modify the previous ciphertext block to flip the appropriate bits. The attacker XORs the previous ciphertext block with both 100 and 999 to determine which bits need to flip. They modify those bits in the ciphertext and send the modified ciphertext to the application. When the application decrypts, the targeted block will now contain 999 instead of 100. The previous block will decrypt to gibberish because of the modifications, but if the application doesn't authenticate the full plaintext, it might process the modified command anyway. The defense against bit flipping attacks is straightforward. Always use authenticated encryption. This means either using an authenticated encryption mode like GCM or ChaCha 20 Poly 1305, or combining CBC with AMAC in an encrypt then MAC construction. The MAC cryptographically binds together the ciphertext and ensures any modification will be detected before decryption proceeds. Without authentication, CBC mode should never be used for security-critical applications. Performance characteristics of CBC mode. Understanding the performance characteristics of CBC mode is crucial for system design and for choosing the right mode of operation for different applications. CBC's performance profile differs significantly between encryption and decryption, and it differs from other modes like CTR and GCM. Let's analyze these characteristics in detail. CBC encryption is inherently sequential. You cannot encrypt block I+1 until you have finished encrypting block I. This is because you need CI as input for encrypting block I+1. This means CBC encryption cannot take advantage of multi-core processors or parallel execution. On a single core, CBC encryption proceeds at the speed of sequential AES operations. Modern x86 processors with AES-NI instructions can perform AES encryption extremely quickly, but the sequential nature of CBC still limits overall throughput compared to parallel modes. CBC decryption, however, can be parallelized. Since all ciphertext blocks are available before decryption starts, you can decrypt multiple blocks simultaneously on different cores. Each decryption operation only needs the ciphertext block to decrypt and the previous ciphertext block for XOR. Both of these are immediately available. This means CBC decryption can be much faster than CBC encryption on multi-core systems, often approaching the throughput of parallel modes like CTR. Memory access patterns also affect CBC performance. During encryption, each AES operation must wait for the previous one to complete, which can lead to pipeline stalls and cache misses. During decryption, the parallel operations can better utilize processor caches and pipelines. However, the need to XOR with previous ciphertext blocks means you can't decrypt blocks in arbitrary order. You must have the previous block available for each XOR operation. Compared to modes like CTR and GCM, CBC generally offers lower encryption throughput due to its sequential nature, but similar or better decryption throughput. However, GCM has the advantage of built-in authentication, which CBC lacks. If you need authenticated encryption, the overhead of computing a separate MAC with CBC often makes authenticated encryption modes like GCM more attractive from both a performance and security perspective. When to use and avoid CBC mode. Given everything we have learned about CBC mode, its security properties, vulnerabilities, and performance characteristics, let us discuss when CBC is an appropriate choice and when alternative modes should be preferred. Making the right choice requires understanding your application's specific requirements and constraints. CBC remains appropriate in several scenarios. First, if you are working with legacy systems or protocols that mandate CBC mode, such as certain versions of TLS or disk encryption standards, you may have no choice but to use it. Second, if you need a well-understood, widely analyzed mode with broad library support across all platforms and programming languages, CBC is an excellent choice. Third, if your application naturally performs more decryption than encryption and can benefit from parallel decryption, CBC's asymmetric performance profile might work in your favor. However, CBC should be avoided in several situations. If you need authenticated encryption and your library supports GCM, ChaCha 20 Poly 1305, or other authenticated modes, these are superior choices because they provide both confidentiality and authentication in a single operation. If you need maximum encryption throughput and have multiple cores available, CTR mode offers better parallelization. If you are designing a new protocol or system from scratch, modern best practices favor authenticated encryption modes over unauthenticated modes like CBC. When you do use CBC, you must follow critical implementation guidelines. Always use a cryptographically secure random number generator for IVs. Never reuse an IV with the same key. Always use CBC in combination with AMAC in an encrypt then MAC construction if your mode doesn't provide built-in authentication. Implement constant time padding validation that doesn't leak information through timing or error messages. And always use a well-tested cryptographic library rather than implementing CBC yourself. The attack surface for implementation errors is substantial. In summary, CBC is a secure and effective block cipher mode when used correctly, but it requires careful implementation and is being superseded by authenticated encryption modes in many applications. Understanding CBC remains important both for maintaining existing systems and for appreciating the evolution of cryptographic engineering toward modes that provide stronger security guarantees with fewer implementation pitfalls. Conclusion and best practices. We've covered a comprehensive journey through AES CBC mode, from its mathematical foundations to practical implementation considerations. Let's consolidate the key takeaways and best practices that every engineer working with CBC mode should internalize. First and foremost, understand that CBC provides confidentiality, but not authentication. This is not a flaw in CBC itself, but rather a fundamental limitation of the mode's design. If your application needs authentication, and most do, you must add it separately. The encrypt then MAC construction is proven secure. First, encrypt your plaintext with CBC, then compute AMAC over the ciphertext and IB. Finally, verify the MAC before attempting decryption. Never decrypt an authenticated ciphertext in security-critical applications. Second, treat IB generation with the utmost care. Use cryptographically secure random number generators. Never reuse IBs, and transmit the IB alongside the ciphertext. The IB does not need to be secret, but it absolutely must be unpredictable and unique for each encryption operation. IB reuse with the same key is a critical security vulnerability that compromises semantic security. Third, implement padding validation carefully and in constant time. Never reveal whether a padding error occurred through different error messages, timing behavior, or any other side channel. Return generic decryption errors and handle all error conditions identically from the attacker's perspective. Better yet, use authenticated encryption modes that do not have padding, eliminating this entire attack surface. Fourth, understand the performance implications of your choice of mode. CBC's sequential encryption makes it slower than parallel modes on multi-core systems, but its parallelizable decryption can be advantageous in certain scenarios. Benchmark your specific application and workload to make informed decisions. Finally, stay current with cryptographic best practices and be prepared to migrate to newer modes as they become standard. CBC has served well for decades, but authenticated encryption modes like GCM and CHA-20 Poly 1305 offer stronger security properties with fewer implementation pitfalls. When designing new systems, prefer authenticated encryption unless you have specific constraints that require CBC. Thank you for your attendance. Please consider subscribing to the channel.